Welcome to episode 5 of Flat Earth Strawman. A strawman is an intentionally misrepresented form of an argument, which is substituted for the actual argument because it's easier to defeat. Taking this approach is a fallacy called attacking a strawman. I will be doing the opposite, exposing the strawman to reveal how it differs critically from the real argument, and then providing support for the real argument. Another definition of a strawman is a person regarded as having no substance or integrity, so the title of this series serves two purposes, as it highlights how little substance there is to the Flat Earth movement and the unprincipled charlatans who propagate it with dishonest tactics. Today we look at what I would call a roast of the recent SpaceX Dragon Demo 2 launch, with a host of the usual suspects: Karen B., Russian Vids, Jaren, Mark Sargent, DITRH, and what I don't think I've ever heard of, Rose 777. I will address several different strawmen from this video, but a few at a time. For now, I'm content to examine DITRH and Karen B's claims about acceleration and escape velocity. The video I'm showing you is courtesy of Gem Panda, who runs the Debate Flat Earth and More Discord server. The link to his video is in the description below, as well as to his Debate Flat Earth and More channel. We'll only be dealing with a few seconds of material from the video today. If you want to watch the complete 90-minute roast of the SpaceX Dragon Demo 2 launch, a link to that video is also provided. We start around 1 minute and 45 seconds in.
G-force planes, are their cheeks supposed to do that?
Yeah, you'd think you'd see something.
I hope we see their cheeks look funny.
They need to accelerate like 200 miles an hour every 3 or 4 seconds.
Isn't it?
So here DITRH claims that the rocket has to accelerate 200 miles per hour every 3 or 4 seconds. And then Karen B will follow up.
Isn't escape velocity 25,000 miles per hour too? They always say that. And they never get anywhere close to that. They don't even get close to 17,000 miles per hour.
So Karen B asks about Earth's escape velocity. She's right that the Earth's surface escape velocity is about 25,000 miles per hour. It's like 25,020 miles per hour. And then she questions the final velocity that the rocket ever achieves. Now we'll skip ahead to about 6 minutes and 20 seconds in, when Karen B reads the speed update. This is about 5.5 minutes into the launch.
It says their speed is over 10,000 miles per hour. It's about to hit 11,000, it says.
Now, she's mistaken kilometers per hour for miles per hour, so we'll keep that in mind for later. So, what can be said about these 20 to 30 seconds of video? First, DITRH does not give an explanation for his claim that the rocket has to accelerate 200 miles per hour every 3 or 4 seconds, so I don't feel beholden to debunk that claim. Instead, I recommend you watch a video of the launch, such as the one here. This will show you the velocity in kilometers per hour during the launch, and you can do some simple math to determine its average acceleration over any period of time you wish. I'll also share a little math secret for converting between kilometers and miles. So the video we're going to look at is this one here. And I have it queued up for 20 seconds into the launch, because that's about when it starts telling us the speed. So 20 seconds in, the speed is 274 kilometers per hour for an average acceleration of about 13.7 kilometers per hour per second. If we jump ahead 40 seconds in, the speed is 691 kilometers per hour for an average acceleration around 17.2 kilometers per hour per second. 1 minute in, 60 seconds in, 1,000 kilometers per hour is the velocity, meaning an average acceleration of 16.7 kilometers per hour per second. Now, if you've been listening to the numbers I've given you, you'll notice that the average acceleration has now dropped. That's because the rocket is reducing its acceleration as it approaches max Q, which is the point of maximum dynamic pressure on the craft. If we go another 20 seconds, the velocity is now 1,524 kilometers per hour at 80 seconds in, for an average acceleration around 19.1 kilometers per hour per second. And you'll notice now that the average acceleration has increased again because max Q has been passed. 100 seconds in, velocity of 2,453 kilometers per hour for an average acceleration around 24.4 kilometers per hour per second. Jumping to 200 seconds in, which is 3 minutes and 20 seconds. Velocity of 6,926 kilometers per hour for an average acceleration of 34.6 kilometers per hour per second. Now, if we jump way ahead to nearing SECO, which is second stage engine cutoff, that would be about 520 seconds in, just short of 9 minutes.
You heard Shannon.
So 8 minutes and 40 seconds in, there we go. Velocity around 25,000 kilometers per hour, which is about 15.6 thousand miles per hour. And the average acceleration at this point is 48.4 kilometers per hour per second. And if we jump ahead to the 9-minute mark, we have second engine cutoff has occurred. The velocity has topped out now at 27,012 kilometers per hour, which means an average acceleration of 50 kilometers per hour per second, which is about 31 miles per hour per second. But at this point, the craft is no longer accelerating. Now, all of these numbers I've been giving you have been dealing with the average acceleration from liftoff to a particular point in time. Instantaneous acceleration is another matter completely. For example, during the last 20 seconds before SECO, the rocket accelerated about 1,800 kilometers per hour in 20 seconds for about 90 kilometers per hour per second of acceleration. Now that is an acceleration closer to the 50 miles per hour or 67 miles per hour that DITRH said was necessary. But as you can see, it wasn't necessary for the entire trip.
Second engine cutoff.
Now for that little math secret I was talking about. If you want to convert between kilometers and miles quickly, all you need to know is the Fibonacci sequence. It is a happy coincidence that the number of kilometers in 1 mile is 1.609344, which is very close to the golden ratio phi, which is about 1.61803399. The kilometer to mile ratio is within 0.6% of the golden ratio. And this means we can use the golden ratio to approximate the conversion between kilometers and miles and kilometers. And that means that we can use the Fibonacci sequence to help, because the ratio provided by each pair of sequential numbers in the Fibonacci sequence approaches phi. So, for example, if you want to convert 89 kilometers to miles, just find the previous Fibonacci number, 55. What if the number you have isn't a Fibonacci number? Well, any number can be written as the sum of Fibonacci numbers. So if you want to convert 70 kilometers to miles, express it as the sum of 2 or more Fibonacci numbers. For example, 55 plus 13 plus 2. You take the previous Fibonacci numbers. 2 is after 1, 13 is after 8, and 55 is after 34. And you have 1 plus 8 plus 34 for 43 miles. So 70 kilometers is about 43 miles. And if you're fortunate enough to be dealing with a multiple of a Fibonacci number, like 130 kilometers, just take that base Fibonacci number, 13, take its preceding term, 8, and then multiply by whatever factor you divided by to get the base, which in our case was 10, and you'll get 80. So that means 130 kilometers is about 80 miles, because 13 kilometers is about 8. Now, if you need to convert from miles to kilometers, just use the next Fibonacci number instead of the previous Fibonacci number. So, for example, 89 miles is 144 kilometers. 60 miles can be written as 55 plus 5, so 89 plus 8 is 97 kilometers. And 50 miles into kilometers, 50 equals, this should be 5 times 10. So Fibonacci number after 5 is 8. So 8 times 10 for 80 kilometers. Now on to Karen B's claims. First, that the rocket needs to reach escape velocity. And second, that the rocket never even reaches 17,000 miles per hour. Let's start with the second claim. She's right, as far as I can tell. The rocket only reaches about 16,800 miles per hour, whereas the speed of the ISS is about 17,130 miles per hour. That's a difference of about 330 miles per hour. It seems much more reasonable to me for the capsule to let the ISS catch up with it, rather than for the capsule to go faster than the ISS to catch up to the ISS. Now, the capsule would need to turn 180 degrees in order to link up with the ISS if the nose of the capsule is where the hatch is. But the capsule has cold air jets designed to allow it to maneuver in such a fashion. And yes, flat earthers, propulsion works in a vacuum. Now, Karen B's first claim, that the rocket never reaches escape velocity, is also correct. But the rocket doesn't need to achieve escape velocity. Why? Because escape velocity is the minimum speed needed for a free, non-propelled object to escape from the gravitational influence of a massive body, that is, to achieve an infinite distance from it. And just below, a rocket continuously accelerated by its exhaust need not reach ballistic escape velocity at any distance, since it is supplied with additional kinetic energy by the expulsion of its reaction mass. It can achieve escape at any speed, given a suitable mode of propulsion and sufficient propellant to provide the accelerating force on the object to escape. Does Karen B know this? If so, she's being disingenuous. If not, she's simply ignorant. A 5-second Google search and a minute of reading is all it takes to address this issue. It's a rocket. It doesn't need to achieve the 25,000 mile per hour escape velocity because it's not a free, non-propelled object. Furthermore, the capsule, the rocket, is not seeking to escape the Earth's gravity completely. When it's in orbit, it is essentially in free fall around the Earth. So it is still subject to Earth's gravity. Many flat earthers claim to understand the heliocentric model, which is why they claim to be able to debunk it. But as DITRH and Karen B have shown us, they either don't understand it, or they have to present a false version of it in order to debunk it. So next time, flat earthers, if you're going to try to debunk the heliocentric model, argue against the real heliocentric model. Don't set up a straw man, because I'll knock it down faster than you can. This is Jeff, realistically speaking.